Do you have any questions from the homeworks? Mia?
Can you just go over how to find horizontal asymptotes again?
Yeah. So if we're looking at like number 23 or whatever, I'm going to do this all in my calculator. So I'm just going to start by typing in the numerator divided by the denominator into my calculator. I'm going to make sure I put a parenthesis around my entire numerator denominator if it's like more than one term. I'm going to choose my window to be between negative 1,000 and positive 1,000. And then I'm going to go ahead and hit graph. So it looks like the horizontal asymptote is there at y equals 1, based on my picture. To confirm that, what I'll do is just numerically check to make sure as I get progressively bigger and bigger x's and then smaller and smaller x's, that I continue to observe that same asymptotic behavior. So I'm going to just test that with the values 10, 100, and 1,000, and then negative 10, negative 100, negative 1,000. So I'll do second trace. Using the value command, I can just plug in. So 10 gives me 1.1. And then 100 gives me 1.01. And 1,000 is going to give me 1.001. And that all looks good, right, as I'm getting continuous, or the whole time I'm getting closer to 1. And I'm staying on the same side of 1, like all those values are above 1. So it looks like it's coming down slowly, approaching 1. So that looks good to me. I'll check the same thing from the other side. So do negative 10. So that's 909. And then negative 100. 0.990. And then like negative 1,000. Oops. I have negative 1,000. I forgot my negative sign. There we go. 0.999, which again is what I'm expecting, right? I have 3 values that are under 1 that are all kind of slowly back increasing, approaching 1. Does that feel okay? So I'm just kind of confirming things, what I see visually, numerically by checking some values. And using those 6 values every time should be appropriate, right? Should be fine. Does that feel okay, Mia?
Yep.
Yeah, no problem. Oh. Anyone else with questions about things? Pardon me. Tired today.
I do have a question for 24.
Okay, what's up?
So, the vertical asymptotes are negative and positive 3.
Okay, that seems fine.
And the horizontal
Yep, that's probably what you observe.
So then,
So if we graph this, doesn't look like anything happened initially, but if you just wanted to check, if we turn off the axis, it did do something. So that just happened to be all on the x-axis is why you couldn't see it. So y equals 0 seems appropriate. You can confirm that by just testing with those same 6x values that we just used. Should confirm that. Is that what you're asking about?
yeah, so to find the horizontal asymptote, you just do this the same way as the previous question,
Mm-hmm. Correct.
even though the amount of lines are going to be different.
Mm-hmm. Yeah. It doesn't matter what the asymptote is. You're just kind of confirming things numerically. So if you think there's an asymptote, which is what we just kind of observed there graphically, okie dokie. Okay. Anybody else before we get going? Okie dokie. Today we're gonna try to do section 1.7, which is a rather large section. So we'll start with a couple of definitions. So we're going to be talking about function operations here. We'll start by defining our 4 most fundamental operations on functions. So let f and g be 2 functions with intersecting domains. Then, for all values of x in that intersection, we define the sum of 2 polynomials, f plus g evaluated at x, as f evaluated at x plus g evaluated at x. The difference of 2 polynomials, f minus g evaluated at x, is equal to f evaluated at x minus g evaluated at x. The product, f times g evaluated at x, is f of x times g of x. And the quotient, f divided by g of evaluated at x, is equal to f evaluated at x divided by g evaluated at x, provided that g of x is not 0. So a couple of things to observe here. So in the definition here, it says that f and g have to have intersecting domains. The reason you need intersecting domains is if you don't, whatever x you pick is going to make at least one of the two functions undefined, and then the problem is kind of impossible because you can't add or subtract or multiply or divide things that are undefined. So all that's the intersecting domains is stipulating is that the problem is possible. Like you do have two things that you could add or subtract or multiply or divide or whatever. And then the definitions here that follow should be kind of, well, these are what we would hope happen, right? If I want to add two functions, it's really nice to be able to go, okay, instead of adding the two functions and then evaluating, I can evaluate the two functions separately and then add them together, which is what we would hope we'd be able to do, right? That makes life much easier if those two actions are equivalent.
What is the symbol between the fraction fx and gx and the
It's a
gx?
semicolon?
The semicolon?
Yeah. So that just saying that, okay, it's, you can divide the two functions provided that the denominator is not 0, right? That's all we're saying there. Just a semicolon. So let's do a couple of examples. So let's say f of x is 2x minus 3, and g of x is square root x plus 2. If I want to do f plus g of x, according to my definition, I'm going to do f of x plus g of x. My definition says f of x is 2x minus 3, and g of x is square root x plus 2. And then all that's left would be to combine like terms or simplify the expression if possible. In this case, what can I do?
Square x squared, x plus 2 and 2x minus 3 to get the square root out of there.
Definitely can't do that. That would be like saying that I can take 2 plus the square root of 3 is equal to 2 squared plus the square root of 3 squared.
Like,
And that's not true.
No, you square both sides is what I'm saying.
Well, it's not really an equation. This is the starting problem, right? You're simplifying here, you're not solving. So you can't square both sides of a simplifying thing, because if I square this, then we're not finding that. You know what I mean? So this is not a solving situation where you can square both sides of, you can do things to both sides of an equation. This is a simplifying situation where you can just, like change the form of something, but it has to be done just to one part. Sergio?
Sorry, I think I missed it when you said it, but why did you use f of x plus g of x?
I mean, that's the definition for a sum of two functions.
Okay, I thought it would be different.
Is that okay?
Yeah.
Okay. Well, it's done, guys. There's nothing to simplify here, right? There's no like terms to combine. You can't add the x's under the radical and outside of the radical, and you can't combine constants and variables. So, that's all. It's trying to be just giving trick questions here. Oh, I'm exhausted too, guys. I mean, I wish. What if we do f minus g of x? Well, our definition above says that I can do this just by g of x minus f of x, right? And then the problem tells me g of x is square root x plus 2, and f of x is 2x minus 3, so I can just write this, right? I hope somebody disagrees, because what I've written is not quite right. Why? Yeah, but they're just just the labels, right? Like if f minus g is f of x minus g of x, then g minus f needs to be g of x minus f of x, right? So that's not the issue. What? Parentheses where? Yeah. So the negative sign here is applying to the entire f of x. So really, I need to have that parenthesis around the entire expression for f of x. And then to simplify, I can distribute the negative. And that would be our final answer, because obviously if we couldn't simplify in the problem before, this is basically the same kind of situation where all I have are things, I don't have any like terms to combine or whatever, right? Good catch on seeing the missing parenthesis there. That makes a big difference, right? And again, I would say that without being reminded of stuff like that, that half or more of us might have made that same mistake of forgetting the parenthesis there, but I would hope that after reminding us about that far fewer of us make that same mistake, right? We're just still coming off the summer, so it's okay. Especially if you didn't see it, it's like, oh, okay, yep, I've done that before. What if we have g times g of x? Well, again, this is a product. So we'll multiply them together. According to this situation, g of x is the square root of x plus 2. Okay. So I can do that. And then can I multiply the square root of x plus 2 times the square root of x plus 2?
Just x plus 2.
Yeah, so let's fill in the blank there, because you pushed past the step that we'll just make sure everybody's clear on why we're getting that. So I multiply those two together. I really have square root of x plus 2 squared. And we know the squared and square root can cancel each other out, giving us the x plus 2. Is that okay to everybody there? Anybody have a problem with that as a final answer? Keep in mind that it's really the absolute value of x plus 2. Remember, after you square something, it has to be a positive value. Now, in this case, you don't really need that there, because the x plus 2 is also underneath the radical. So you know that that also can't be negative if the x plus 2 is under the radical. So we don't really need that there, but technically speaking, when you square something and then square root it like that, or vice versa, you end up with a positive result. But that was okay. So let's say we have f divided by g of x. So again, according to our definition, that's f of x over g of x. And if we plug in the values for this problem, that's 2x minus 3 over the square root of x plus 2. Anything more you want to do with this? What do you guys think? Elvis?
You multiply the top and bottom by x.
Yeah, so most of us have probably been taught here to rationalize the denominator by multiplying the top and bottom by root x plus 2 in this case. Doing that, I'm going to just write the numerator as a product. You could distribute the root x plus 2 through if you'd like, but you don't really need to. You can just write it as a product there, is fine. Because most of us along the way have been told that we aren't going to leave a radical in the denominator of a fraction, right? So one of the things you'll find as you progress further through mathematics is that some of these like preferences become less of a requirement and more kind of if it's convenient. This is one of the first things that kind of gets shed as you go deeper through mathematics. For this course, what I would ask from you guys is that if we're talking about an expression that involves a constant in the denominator, so like 3 over the square root of 2, that's something that I would like the denominator rationalized. But if it's something that involves a variable expression, you can leave it. I think would be probably best for this course. Occasionally you'll get something, on a problem like this that might be kind of horrific to deal with, the radical in the denominator, and just we're going to be good with just worrying about it for constants, I think. Fair enough? So if you went ahead and did it, I would certainly never mark it wrong if you did that correctly. If you continue to rationalize the denominator and you did it correctly, would certainly not be wrong. Would never do that. But I don't think that it's necessary. So these are the 4 fundamental operations on functions, because these also have analogs to operations on real numbers, right? We can add, subtract, multiply, and divide real numbers as well. There's a 5th operation for functions that doesn't have an analog to the real numbers. That 5th operation is called composition. So let's define what we mean by that. Oops. So let f and g be functions such that the domain of f intersects the range of g, then the composition of f and g is so the notation that we use is we use this open circle here. The way we read that open circle symbol is the word compose. So that's like an open multiplication dot. It is not the letter O. So the way you'd read that set of symbols there is f compose g of x. You don't read it fog, please. It makes me want to stab myself in the ears when I hear people call it fog. So that's f compose g of x. And what this means is f of g of x. Is that we're kind of inputting one function inside of another. The reason why we have this restriction that the range of g intersects the domain of f is because the output of g of x has to be a valid input to f, right? So whatever g of x is, that range value has to be a part of f's domain because that's what we're plugging into f. Does that feel okay? Again, all that domain intersecting the range nonsense is just to make sure that the problem is possible. So let's do a couple of examples. So let's say f of x is 2x squared minus 3x, and g of x is negative 3x plus 4. Let's run through a couple of examples here. So let's say we want to do f compose g of x. From our definition, this is f of g of x. Cool? From the problem, I know that g of x is really negative 3x plus 4. From what I know about function notation, I know that when I have a function notation, what it's telling me to do is take whatever's in the parentheses and substitute it in for my x's, right? So I'm going to write 2, and then in place of x, I'm going to write negative 3x plus 4. Then I have squared minus 3, and then in place of x, I'm going to write negative 3x plus 4. So far, so good. Okay, so the composition at this point is done. What I still should do, though, is there's quite a bit of simplifying that could be done at this point. So let's continue to kind of clean this up and do the simplification. According to the order of operations, the first thing I should worry about is the exponent. So how do I do negative 3x plus 4 squared? Eddie? You have to FOIL this out, right? Negative 3x plus 4 squared really means negative 3x plus 4 times negative 3x plus 4. So if you FOIL that stuff out, I'm going to skip writing down all of that. But you end up with that trinomial. Is everybody okay there? Now that we've dealt with the exponent, the next thing I would do is distribute. Yeah, do the multiplication. So I can distribute the 2 through and the negative 3 through. And then I can just combine the remaining like terms. And that would be my final answer. let's do then G compose f of x. So again, for my definition of composition, that would be G of f of x. In this problem, we defined f of x as 2x squared minus 3x. And then, according to my definition of function notation, I'm going to just substitute that expression in for all the x's in G of x, which gives me this. Everybody happy with that? At this point, the composition is done. We just have a little bit of simplifying to do. Much less than the previous problem, though, right? So here, all I need to really do is distribute through, and then there's no like terms to combine. So I am done there. So far, so good. So an important observation here, notice that these two answers are not the same, right? So that leads to the important observation that composition is not commutative. That the order in which you do the composition definitely matters. You're not going to get the same answer, typically, regardless of the order of the composition. Everybody's okay with that? Now, when the composition does give you the same result, that tends to be a special situation. And of those special situations, there's one particular that is of interest to us, and we're going to define that situation right now. So we say that if f and g are two functions, we say g is the inverse function of f if and only if the composition at g compose f of x is equal to the composition f compose g of x, and both of them give me the value x. So what this definition is really saying is if I take an input, x, and I do the function f to it, and then I take that result and do the function g to it, if it returns the original input x, then f and g were inverses, regardless of the order in which you use f and g. Right? That basically the one function is just undoing whatever the other function did. Does that feel okay? So notationally, we write this g of x as f inverse of x. So that -1 in the exponent doesn't mean the same thing as like a -1 exponent on a variable or constant. When we write the -1 exponent on a function, it doesn't mean a reciprocal. It means the inverse of the function. So something that has this property of like canceling the other function out. So let's talk about like writing some inverses. Sound good? Okay. So let's say we have a mapping diagram. If I wanted to write the inverse for this, well, I need in the original function, 1 goes to 4, and then 2 goes to 6, and 3 goes to 5. In its inverse, I need to take 4 and send it back to 1. I would need to take 5 and send it back to 3. And I would need to take 6 and send it back to 2. Everybody feel okay on that? So basically, we're just reversing the direction in my mapping diagram, right? Okay. What if my function instead was a set of ordered pairs? So if I try to write my inverse, again, I'm going to kind of reverse the direction here. So in my first problem, I have that -2 goes to 4. For my inverse, then I would need to take 4 and send it to -2. In f, -1 goes to 6, so the inverse has to send 6 back to -1. I have 3 goes to 8, so I need to send 8 back to 3. And I have 5 going to 8, so I need to send 8 back to 5. We okay there? Do you notice anything odd about this f of x? Or sorry, f inverse of x? Lexi?
It's not a function.
Yeah, it's not a function. What did you notice that told you that?
That every x has a unique value.
Yeah, is that we have an x-coordinate that's used more than once, right? Now, the previous inverse we found, that was a function, sure as sure can be. This one was not a function. Let's just kind of tuck that away in the back of our head for a minute, that these inverses are not necessarily functions. We'll have to be careful about kind of what we're doing, but we'll get back to that. What if we have a function represented by a graph? I can do a better job of drawing than that, can't I? Nope, apparently not. What if I want to generate an inverse from this? I'm going to try one more time to draw that a little bit neater. And marginally at best. I think the easiest way of going about this is to go and pick a couple of points off of our graph. So let's say that this point is maybe like, let's say maybe -4, 4. This point maybe is 0, 3. Oops, 0, -3. And this point here maybe, let's say, was 2, 0. What I'm going to do now is I'm going to transpose those points and plot them. So 0, -3 is going to be written as -3, 0. And then 2, 0 would be written as 0, 2. And then -4, 4 would be written as 4, -4. Is everybody okay there? So the vertex in F should still be the vertex in F inverse. So my inverse would look something like this. Everybody okay with that? The other way of thinking about this is if you think about the line y equals x. F inverse is just a reflection of f of x across this line. So like this part of f makes that part of f inverse when we reflect it. Or this part of f, oops, thought I picked a different color there, would make like this part of f inverse when we reflect it. And then like this part makes like that part when we reflect it. So I think it's easier to do the points, which is why I showed you that first, but it's worth mentioning that you can do it the same way. What do you notice about this F inverse again? Not a function, right? So let's talk about how to kind of tell if something's a function or will be a function or not. Tell if a function's inverse will be a function or not. Ideally, we'd like to be able to do that without having to find the inverse first. We'd like to just be able to look at our function and then make a determination. And it is possible to do that. In order to do that, though, I need to define a couple of things. So there's a couple more properties of functions that we need to define. So the first one is the term onto. And some people also use the term surjective. Onto and surjective can be used interchangeably. Onto is probably the more commonly used term, but probably not by much. We say that a function is considered onto if every element in the range is mapped to by some element in the domain. The next term is one-to-one. And again, the alternative term for one-to-one is injective. Again, one-to-one is probably the more common one, but probably not by that much. We say that a function is one-to-one if every element in the domain maps uniquely to distinct elements in the range. And then the last term here is bijective. And we say a function is bijective if it's one-to-one and onto. Yes, sir. Of course. In just a moment, we'll do a couple of examples to illustrate how you can look at a function and tell if it has any of these properties. We'll do a couple of mapping diagrams, and we'll do a couple of graphs. Okay? So let's say we have this mapping diagram. Okay. So this function here is not onto because we have some things in the range that are not used. In this case specifically, it's the number 6. Okay, so onto just means the entire range is used. We would say that this function is also not one-to-one, because we have some range values that are used by more than one domain value. In this case, 5 is paired with 2 different domains. Everybody okay with that? Let's say graphically, we have a function that looks like a parabola. This function, again, is not onto because there's some y values that are not used by the function. And it's not one-to-one because the y-coordinate, whatever this is used by 2 different x-coordinates. Is everybody okay with that idea?
Sorry, what is that one?
Well, this is like the point x1y, and this is like x2y. That same y-coordinate is used by 2 different x's.
Okay.
Is that okay? So again, same situation as the mapping diagram, we're looking at a graph, right? I'm still kind of thinking about it the same way. Now, let's look at some examples that are, one-to-one but not onto, or onto but not one-to-one, or that are both. Okay, so I'm going to draw some graphs. So an easy one, this graph is both one-to-one and onto. Every y value is represented by some point in the function, and no x values use the same y values, right? Everybody happy with that? Okay. This function would be one-to-one, but not onto. Easy to see that there's some y values that aren't used by any point in the function, but the y values that are used are only used by one x value. And let's say we have this. Is onto, but not one-to-one. Right? You can see that all the y values are used. We have an arrow going up and an arrow going down, right? So all the y values in between get used. But there's lots of places where one y value is used more than once. So for example, right along here, we have one y value that's used more than once. Nope, I mean y value, right? That'd be like x1 comma y, x2 comma y, x3 comma y. They're all the same amount up. So we have these properties here. As far as we're concerned, which one is the major contributor in determining whether the inverse will be a function or not? Will it be the one-to-oneness or the onto-ness? It's the one-to-oneness, right? Remember when we change something from a function to its inverse, we're swapping the x's and y's. If a function uses one y coordinate more than once, its inverse then, that y coordinate becomes an x that's used more than once. And we'll have something that fails a vertical line test almost by definition, right? Now, that's going to be the major takeaway for us. I want to say, though, that the onto-ness is can still cause a problem in like an inverse being a function, but it's kind of beyond the scope of this class as to like why that would or how that could happen. Not something that I would expect you guys to deal with, and we're not going to talk about it right now. So technically speaking, we say that if f is bijective, then f inverse is a function. And mostly for us, really what we need to check on f is just that it's one-to-one, right? That's the part that really is going to matter to us. And if I'm checking for something being one-to-one, the easiest kind of way to do that is just doing like one of these horizontal line tests to see if there's a horizontal line that intersects the graph more than once. That's kind of my go-to to determine whether one of these functions is one-to-one. And then if it is one-to-one, its inverse should be a function. If f is not one-to-one, f inverse would not be a function. For our purposes, let's be clear. Does that feel okay to you guys? Okay. There's one more form or representation for a function that we haven't talked about how we write the inverse for, and that's a function that's given in function notation. So the rest of our time here, we're going to just burn through some examples doing this because it's also a good review of some of our Algebra 2 content. So if I have the function f of x equals 3x minus 7, and I want to find the inverse for this function, I'm going to start by replacing the f of x, or the function notation, with just the y equals. And then what I'm going to do is I'm going to get the x variable by itself. So in this case, I'm going to add 7 to both sides. And then divide by 3. And then you could write this as one fraction like I have, or you could write it as like y over 3 plus 7 over 3. That's fine also. Doesn't matter to me. Once we've isolated the x, we're going to swap the x and y variables. And then really you could write this now as f inverse of x. Everybody okay there? If we ask to verify that these two things are indeed inverses, what we need to do is we need to show that f compose f inverse of x is equal to x, and that f inverse compose f of x is also equal to x. So when I substitute that into f, I get that. Everybody agree? Well, I have a multiplied by 3 and a times 3, so those cancel out. And then I have a plus 7 and minus 7. Those cancel out. And we have just x. Yes?
Where did the 3 outside parentheses come from?
So remember that in this problem, f of x was 3x minus 7. So like that's where the 3 and the minus 7 are coming from. That was just the example that we used. And if we do the other direction, we do the composition, we have 3x minus 7 plus 7 over 3. Well, minus 7 and plus 7 add to give us 0. And 3 over 3, reduce, and we're left with just x again. So since each of those compositions gives us x, we know that these two functions are inverses. That's my verification process. Is everybody okay with that one? Finding this inverse was not terribly challenging. Let's look at some more examples that are a little bit tougher. Let's see. G is the next letter in the alphabet. So let's look at this rational expression. What makes this one more difficult than the previous example? Yeah, we have x's in two different places. Very good. So just like before, I'm going to replace the function notation with a y. And my goal here is going to be to get the x's by themselves on one side of this equation. I think the easiest way to start is to like cross multiply to clear the fraction out of there. Is everybody okay with that? I'll distribute the y through then. And now I'm going to move the things with the x's onto one side by subtracting 5xy from both sides. And then move the 5 to the, or the non-x's to the other side by subtracting 5 from both sides. Now if I look at the left-hand side of my equation, both terms contain an x. That means they both have the greatest common factor of x. When I factor that greatest common factor off, I'm left with 2 minus 5y. And that's the trick, that I've taken the x from being in two locations to being in one location. So now I can divide both sides by 2x minus 5y. And the last step would be to swap my x's and y's. And if it's me, I probably do a little bit of cleanup here. If I multiply the top and bottom by -1, I get a slightly simpler answer because I get rid of a bunch of negative signs. Those are x's. I swapped and then wrote it as a function notation all in the same step. Is that okay, Drake?
Yeah.
Okay. Let's check that this is an inverse as well. Actually, we'll do just half of the check because this one is quite a bit more challenging and time-consuming. So let's just do this real quick. So here, I'm going to plug in f of x for x. And I meant f inverse of x for x, excuse me. And then woof, that looks pretty rough there, right? Well, here's the trick that I would use in this situation, is I would like to start by getting rid of the fraction inside of other fractions. If I look carefully, the fraction inside of my big fraction has the same denominator. So I'm going to multiply the top and bottom of this fraction by that same denominator. So when I distribute it through, some nice stuff happens. So it cancels with the denominator in that first fraction, leaving only the numerator. Which is a lovely, lovely result. Everybody see what happened there? And that's a pretty great time saver rather than like distributing the 2 and the 5 and then making a common denominator and adding fractions and like, it'll get you to the same spot, but woof, that knocked out the need for common denominators and fractions and all of that nonsense all in one step, which is pretty righteous, you know, my dudes. So now I'll just distribute things through. And I'm left with just 41x over 41, which is just equal to x, which is what I was hoping to have happen. If you did the check in the opposite direction, the work is really very similar. It's the same tricks. It'll work kind of the same way. I'm not going to do it in the interest of time. I'm going to skip a couple of my examples that I've written down and go straight to the couple that I think will be the most problematic. Let's see, what letter are we on now? C, and that would probably be H's. Or did I call, yeah, this was supposed to be obviously g. Sorry. So let's say we have negative 1/2 of 3 to the 4x. So we'll start by just replacing the function notation with a y. Then what do I want to do first for a situation like this? Again, I'm trying to get the x by itself. So what should I do as my first step to get the x by itself? Amy? Very good. Yeah, let's get the fraction moved over to the other side. So dividing by 1/2 is the same as multiplying by -2, which is the way I'd prefer to think of it as well, rather than dividing by a fraction. Yuccaronis. Okay, the next thing we need to do is what? We got to get rid of that 3, right? How do we get rid of that 3? What'd you say? Yeah, very good. Which log should I use? Log base 3. Yeah, the base of my logarithm should match the base of my exponential. Very, very good. Again, this is something that we covered last year in our Algebra 3-4 course. Now, I wouldn't expect everybody to remember that straight away, but that's why I wanted to get to this and do a reminder, because I would guess that 50% or so of us were like, ooh, darn it, yes, okay, a logarithm. Would have taken me a long time to get there, to realizing that's what I needed. And then my last step would be to just divide both sides by 4. I'm going to choose to write it as multiplying by 1/4, as I think it makes it a little bit more clear what is getting divided by 4, that the logarithm happens before the division. And then if we swap our variables and rewrite it in function notation, we have this. And I'm going to try to squeeze in one more quickie example that has a logarithm in it. Just to review that as well. So remember that ln is the natural logarithm. It is a type of logarithm. First step I'm going to do is multiply both sides by 3/5. And then I got to cancel out that natural log. What do I use to cancel out a natural log? Exponent base. What is the base? E. The natural log's base was E. It's like I expect you to remember the stuff we did last year or something. And then I can just add 1 and divide by 7. And if I write this then as my inverse after swapping the x's and y's, There's my final answer. Yummy jummies.
Good afternoon, Notre Dame teachers and students. Let's pause